So maybe at this point you could outline what the Szemere partition is.
So Szemere partition means that if you have a large graph, then you can partition the vertex set into a certain number of classes, where the number of classes is not too large, it is really bounded by something. And if you consider the edges between two classes, this is very much random-like. So which means, which is a very surprising fact, that an arbitrary graph which is large enough and which is dense, so all what I am saying refers to dense graphs, which means that these have constant times n square edges. You have finitely many pieces where all the edges behave like random graphs. So means that one can build up an arbitrary graph from not too many random-like graphs.
And can you now indicate somehow how this connects up to the limit concept?
What does it mean that a graph sequence is convergent? And it can be formulated in different form. One is that the Szemere regularity partition converges. Another is that the density of small subgraphs converges. And the other is that the edge distribution converges in certain sense. And of course, not all these graphs are random or random-like. So for a general class of graph sequences, this is true. And what is a surprising fact, that these three properties, edge distribution, Szemere partition, and small subgraph frequency, are equivalent properties, so with in proper quantitative form, equivalent properties of quasi-random graphs. These properties are really glued to each other in a much more general world than just quasi-random graphs.